So we've dealt with solving inequalities, whether it took one step or more than one step. But now we're going to talk about compound inequalities. Because the truth is, an inequality is kind of a boundary. It creates a boundary for things. And sometimes there is just one boundary, meaning there's just a maximum or just a minimum. But there's also times when there's more than one boundary. And that's really what gets reflected in these compound inequalities. Now we'll deal with two kinds. The first one is called the AND type. So they take two forms. One is where you see two inequalities, two separately written inequalities, with an AND in between. Now, when you see one written, it obviously has two inequality signs, but it's written just as one statement. This is also understood to be an AND type. So you'll either see the word AND, or you'll see two strung together into one like this. Okay, so you can see here the way it's done. The graphing is the main way we do it. We're not solving very much here. There'll be a little bit of solving, but not very much. It's mostly just making sure you graph it correctly. So on this one, it says 2, and we put an open circle because it's just less than, and we shade it to the left. So this represents the graph of x is less than 2. Then x is greater than or equal to -1. So we put a closed dot on -1 because the or equal to, and we shade it to the right. So then you look at these two together. That's what they did with these dotted lines. They said, all right, so now since it has to be true that this is true and this is true, we can only graph as our final answer where they overlap, which the math word for there is their intersection, but that's where they overlap. Like you think about two roads coming at a stoplight. We call this part the intersection of the roads because that's where these overlap. You know, if this is Redbud right here, and this is Wilkinson or Franklin, this spot in here is where the two roads are one. It's where they overlap. So, you'll graph just like this. I am not going to require you to write the answer in this form, so you will just have to show me the graph correctly for these types. Okay, so I want you to also see how we do it when they set it up as one long string like this right here. So essentially, while they put it in as one, we're going to separate it into two pieces. So first, we ignore the less than 3 part, and we say, all right, let's just look at -1 is less than x plus 2, which you can see they did right here. They solved it by subtracting 2 from both sides, so they get -3 is less than x, or we'd normally write it x is greater than -3, which you can see they wrote that way right there. So open circle at -3, shaded to the right. Then they say, all right, we're going to ignore the left part and just look at x plus 2 is less than 3. Because this really is two separate statements just combined into one. It's saying x plus 2 is greater than -1 and x plus 2 is less than 3. So again, we ignore this part and just write this inequality. Subtract 2 from both sides, and we get x is less than 1. So we graph that. We have an open circle at 1 and shade to the left. And you can see where they overlap is from -3 to 1. And one thing I think I forgot to mention on this first example, you do imitate whatever kind of dots you had on the original graphs. So these are both open. So on our final answer, they're both open. On this one, it was open on 2, closed on -1, so we kept it that way in the answer. Closed at -1, open on 2. Okay, so let's try it. Graph the solution set of each compound inequality. So I'm just going to draw it below them just so we can kind of get a picture that way. Then we'll put the final answer on the actual graph. So first they tell us b is greater than -1. So I put an open circle at -1 and shade to the right because it's greater than. Then it says b is less than or equal to 3. So I put a closed circle at 3 and shade to the left. So you can see, and you don't have to draw these lines unless you want to, but you can see these, this is where they overlap. They overlap from -1, which will keep an open circle, to +3, where we'll have a closed circle, because we want to imitate that, and we connect the two. So essentially, our answer has to be between -1 and 3. It can be 3, but it can't be -1. Okay, so on number 2, let's split this up. So first, we'll look at just 2 is greater than or equal to q, or another way to write it would be q is less than or equal to 2. So we put a closed dot on 2, and we shade it to the left. Then we look at this portion. So the middle gets used in both of them, but the ends, the left side and the right side, just get used once. So that's q is greater than or equal to -5. So I put a closed dot at -5 and shade to the right. So you can see the range is from -5 to +2. And both of them have closed circles, because this is where the two intersect. This is where they are both true. And means both have to be true. So for example, if you're a guy, you might have decided the person you're going to be married to must be a Christian and a woman. You're not going to find a Christian and not care about their gender and say, that's fine, they're a Christian. Or you're not going to say, oh, it's a woman, I don't care if they're a Christian or not. If you've decided you want to marry someone who is this and this, it means they must be both. Okay, we'll do this one. X is greater than -3. So we put an open circle at -3 and shade to the right. X is less than or equal to 4. Put a closed circle at 4 and shade to the left. So we can see we put an open circle on -3, closed circle on +4, and connect the two. Okay, sometimes there is a little bit of solving we have to do. So when it's just one step like this, it's usually pretty easy to just keep this combined. So like here, I have 4 is less than w plus 3 is less than or equal to 5. So I know I need w by itself, like we had up here, the q is by itself. Actually we had to solve this one. And we'll subtract 3 from every piece, so from all 3 pieces. So 4 minus 3 is 1. Now w is by itself. And 5 minus 3 is 2. So if I take this piece, I get w is greater than 1, because I'm flipping the order so the w is on the left. If I take this piece, I get w is less than or equal to 2. So we have it greater than 1, so we have an open circle here, go greater. And we have a closed circle at 2, and go to the left, because it's less than. So you can see this overlap is pretty small. It's only from 1 to 2 that these two overlap. So we can imitate the same thing here. Since this is just a one step to solve, it's pretty easy for us to just write it. And then we can add 5 to every piece. So all 3 pieces we need to add 5 to. So -3 plus 5 is +2. These cancel, so we just have p. 2 plus 5 is 7. So this piece, I'll switch it around and say p is greater than or equal to 2. This piece, I'll leave it as it is and say p is less than or equal to 7. So we have a closed dot at 2, and go greater than, closed dot at 7, go less than. So the overlap is from 2 to 7, and both have closed dots. Okay, 6. These are separate, so you'll just handle them separate. So we'll add 2 to both sides here. Get n is greater than -1. So open circle at -1, shaded to the right. Here we'll subtract 4. So we get n is less than 2. So open circle at 2, shaded to the left. So we go open circle here to here. And connect the dots. Okay, now this is the hardest one of the bunch. And this one I would not try to solve all at once like we did with number 4 and number 5. There's way more than one step going on here. We've got variables on all sides. So this one is really important to actually separate them and deal with them individually. So first I'll do the left side with the middle. So d minus 3 is less than 6d plus 12. Since I want the variable to be on the left anyway to help me graph, I'm going to choose to subtract 6d from both sides. And I get negative 5d minus 3 is less than 12. Then I add 3 to both sides and get negative 5d is less than 15. Then I divide both sides by -5. And I do have to flip the inequality sign because we divided by a negative. So we get d is greater than -3. So open circle, open circle at -3, and we go to the right. So now we'll do the other half. I'll give myself more room this time. And we'll subtract 2d from both sides. Subtract 12 from both sides. And divide both sides by 4. So we get d is less than 5. So open circle at 5, shade to the left. And so this has an open circle at -3 and at 5, we connect the dots. Now before I go show you the OR side, so we have two kinds of compound inequalities. One is AND, which is what this side of the page is about. The other is OR. There's a circumstance that didn't come up in these examples that I want to show you. You could have something that says like x is greater than 3 and x is less than -1. Okay, so let's think about how that would be graphed. X is greater than 3. We put an open circle at 3, shade to the right. X is less than -1. Put an open circle at -1 and shade to the left. Oh. You see, these never overlap. These never intersect. If that happens where there's no overlap, then you say there's no solution. Or you can do the 0 with the slash through it. You can write either one of these, no solution or this symbol. So that can happen when there's no overlap between the two inequalities. It's impossible for something to be bigger than 3 and less than -1, so there's no solution to this. All right, stand up if you need to, take a deep breath. We'll do the OR side. Now, this is a very important thing to understand. In math and in logic, OR works if one or both are true. So you might say, the person I want to marry it's really important that they have brown hair or brown eyes. So think about it. If you're truly fine with either or, if you meet someone with brown eyes and blonde hair, you're like, cool, that checks out, they've got brown eyes. Or if you meet somebody with green eyes and brown hair, you're like, cool, they got brown hair. But if they have both brown eyes and brown hair, that's not a problem. That also fits the bill. So, the graph of a compound inequality containing or, the math word for it is the union of the two. So it's not where the two overlap. It shows everywhere both are involved. Because if either one of them are there, we're good. So let's see an example here. We have 2a plus 1 is less than 11, or a is greater than 3a plus 2. So you can pause and see how they solved it if you want to. You subtract 1 from both sides, divide both sides by 2, and get a is less than 5. So I know it's hard to see because of the dotted line, but that is an open circle on 5. Then shade to the left. And then they solve this one. You subtract the 3a over, get negative 2a. Divide both sides by negative 2, flip the inequality. Your a is less than negative 1. So they have an open circle at negative 1 is shaded to the left. So with and, we look where the two of them overlap. So if this was an and question, we could only shade this part right here because that's where they overlap. But an or question is where either of them or both is true. So since this one goes all the way back to 5, and then both of them go down to negative infinity, we can start our answer here at negative 5 and go down as far as you need to go. Because that's the union of the two. It's almost like you took this line and you squeezed them together and showed where either one of them is true. And we get this answer here. Okay, so let's do it similar to how we did the last one. We'll just draw below and then look at the union where either or both is true. So b is greater than 2, open circle to the right. B is less than or equal to negative 3. So closed circle to the left. Okay. Now you remember what I said. If this was an and question, we'd say no solution because they don't ever overlap. But with or, they don't have to overlap. It's okay if just one of them is true and not the other. So we actually just combine these into one graph, put an open circle, go to the right, put a closed circle at negative 3, and go to the left. Because it's okay if this is true or if this is true. They don't both have to be true. Number 2, Q is less than or equal to 3. I'm just flipping this around to make it easier to graph. So we put a closed circle at 3 and shade to the left. This is Q is less than or equal to positive 1. So we put a closed circle at 1 and shade to the left. So this is similar to what we saw up here. This one, the one that's less than 1, overlaps everywhere with Q is less than or equal to 3. But they don't both have to be true. It's fine if either one is true. So we want to expand and show the union of the two. It's like we're combining them into one line. So we'd have a closed circle at 3 and shade all the way over for this answer. And these are the two most common forms of answers you're going to get with ORs. It's either going to be two lines going the opposite directions because they have no overlap, or you're going to just have a point, you could call it a ray, but a point and then a line going just one direction because they both go the same direction, but obviously one's going to be a little higher or a little lower than the other as far as its endpoint. So 3, y is less than or equal to negative 4. Closed dot at negative 4, we shade to the left. Y is greater than 0, open circle at 0, shade to the right. So this is very similar to number 1. They never overlap, but that's okay because we're going to combine them together. open circle there, and shade to the right. Okay, here we have to do a little bit of solving. So this one, we divide both sides by 3. We get 1 is less than W, which is the same as saying W is greater than 1. So I put an open circle at 1, shade to the right. Here I divide both sides by 3. I get W is greater than 3. So I put an open circle at 3 and shade to the right. So this is one where they overlap a whole lot with each other, but we have to unify them into one. So it's just like you're shifting this line up here. So we put an open circle at 1 and shade to the right. And one question you may have is, well, wait a minute, shouldn't there be an open circle on 3 because this one doesn't exist at 3? If you thought that, that's a great question. But this line fills in that circle because both don't have to be true, just one or the other. So 3 does work for this one because 3 is greater than 1. 3 is not greater than itself, so it doesn't work for this inequality. But as long as it works for one or the other, then we're good. Okay, number 5. We'll subtract 1 from both sides. Divide both sides by 3. We get P is less than or equal to negative 4. Oh, sorry, I dropped the negative here. So I made a couple mistakes. Sorry, this should be negative 3P. So we divide by negative 3. So feel free to pause and fix my mistakes. Sorry about that. So we divide both sides by negative 3. So because we divided by a negative, we do have to flip the inequality sign. And negative 12 over negative 3 is positive 4. So close dot at 4 and shade to the right. Thankfully this one's simple. It's already written for us. P is less than 2, open circle at 2, shade to the left. So this one, we just combine them and we have 2 lines going opposite directions. All right, this has been a long one. We're almost done. We subtract 4 from both sides. We get 2x is less than or equal to 2. Divide both sides by 2, and we get x is less than or equal to 1. So I put a closed dot on 1, shade to the left because it's less than. Okay, on this one, I'm going to subtract 2x from both sides. Get negative 1x is greater than or equal to negative 4. Then I'll divide both sides by negative 1, which means I'll have to flip the inequality to be less than or equal to. And negative 4 divided by negative 1 is positive 4. So we'll put a closed dot at 4 and shade to the left. So this is one where they overlap a lot. The biggest we can go, though, is 4. Then we shade everything to the left. That is the union of the two. It's where either one of them, or both, is true. Oh, all right, last one. We'll start by subtracting 2 from both sides, giving us 3a is greater than or equal to 3. Divide both sides by 3. We get a is greater than or equal to 1. So closed circle at 1, shaded right. Okay, over here, I would start by subtracting 2a from both sides. Make sure you don't miss this 7 right here. So we have 7 plus 1a is less than 6. I subtract 7 from both sides. Get a is less than negative 1. So open circle at negative 1, shade to the left. So these two don't overlap, so we just write them as 2 separate rays. And in case you haven't heard the word before, a ray is when you do have a stopping point on one side, but it goes on forever on the other. So this by itself is a ray. This by itself is a ray.